Good afternoon. Thank you for signing up for Introduction to Digital Signal Processing. I'm Alan Downey. I teach at Olin College, which is a new engineering school. It's just outside of Boston. We started up about 15 years ago. We are trying to fix engineering education. And one of the ways that I'm working on that project is to try to take a computational approach to some of the topics that have been traditionally taught using a very mathematical approach. And the theory is that if you know how to program a little bit, that is a pedagogic lever. It's a tool that you can now use to learn everything else. And in particular for digital signal processing, I think it's a really good fit. So again, if you have got everything set up, you should have these two links. The first link will take you to the instructions for all the setup, downloading my repository, and getting Jupyter set up with the packages that you need. And the second link there is these slides. So if you want to grab the slides, I think you'll find it useful if you have one window with Jupyter running and another window with my slides. I think that'll help because if you get out of sync with what I have up on the front here, you can get to whatever slide you want to. The other thing I'm going to recommend, if you're feeling social, make friends with whoever is next to you and think about doing a little bit of pair programming. So if one of you has the slides and the other one has the notebook, a lot of this stuff, if you are thinking and programming at the same time, it makes your head hurt. So have somebody to talk to. Everybody got that URL? So that's the tiny URL, capital DSP 17 tutorial, TUT. All right. So we were talking a little bit before the session started that this is a slightly crazy attempt to take a one-semester class and go through it in 3 hours. And I think we can do it. I think we can get a level of understanding that I think is interesting and useful. It's not going to be super deep. So this is a little bit of a taste. I hope it'll give you an overview of what the big ideas are and stimulate your appetite to learn more about this. That's the goal. Why is that I think some of this stuff, signal processing in general and Fourier Transform in particular, is the coolest thing I know. I think about it all the time. I enjoy teaching it. When people learn this for the first time, light bulbs go on. It's just great stuff. It's useful. It's used in a lot of domains. Obviously in electrical engineering, it comes up anytime you're taking data off sensors and things like that. But it's also time series analysis of any kind of statistical stuff. It's audio processing. It's in 2 dimensions, things like image processing. So tons of useful stuff. The algorithms themselves are these really elegant pieces of mathematics that when you start to understand them at many levels of depth, just get richer and richer. And the other is that it explains a lot about how we perceive the world because most of our senses are doing things that are very much like signal processing. The thing that makes me sad is that most people don't know about this stuff. If you're not an engineer, you probably haven't studied this at all. If you are an engineer, you probably studied it, but you did it the hard way. And this is a good book. It's a very popular book for digital signal processing, but it starts with a lot of mathematics, and it takes a long time before you get to what I think is the good stuff, the applications, the examples that you can really see and hear. I think this is the painful way to go at it. I think with Python, you can have a lot more fun. I think it's just entertaining. And in particular, the examples that we're going to use today use sound. Again, the reason for sound is that our ears are doing something very much like what the Fast Fourier Transform does. When we hear a sound and identify pitches, like musical notes, what we're doing is something like spectral analysis of the signal that's coming into our ears. If you get a chance, later on, not now, click on that link. Vi Hart, who is a mathematician who publishes a bunch of videos on YouTube that are really excellent. I think you'll enjoy her stuff. But in particular, this video is about how noise works, how sound perception works. So check that out when you have a chance. And of course, the nice thing about Python is that we have tools like Jupyter that let us work with this stuff very interactively, and that's what we're going to do. Most of what I'm talking about today is part of ThinkDSP. This is a book that I published under a free license. So if you go to Green Tea Press, you can read the book, you can modify the book, you can pull out excerpts. It's under a free Creative Commons license. It's also available from O'Reilly Media, so if at some point you'd like to have a hard copy and read that, you certainly can. First thing I want to do is the example that I was pointing you to a minute ago. This is the time when you should, first of all, put in your headphones. Second, if you have not already cloned the repository, do, although I hope you have because it's kind of big and the network is kind of slow. Fire up Jupyter and then open up the Chapter 10 preview. And if you like, I'm going to run through that process one more time up here. So if you're just opening Jupyter Notebook, I'll show you how that looks. I'm going to close this. And close this and go back to my command line and shut down the server. And again, the directory that I'm in, I'm going into thinkdsp.com, sorry, thinkdsp, and into the code subdirectory. If you just do an ls, you'll see all the files. There are a bunch of notebooks there. There are a bunch of Python modules. We're going to be using thinkdsp.py, which is a library that wraps some of the functions that are in NumPy and SciPy. And there are a bunch of recorded sounds there that are in there as wave files. So if you launch Jupyter Notebook, Jupyter, it should open up a browser. If it doesn't, you will see one of the things that Jupyter outputs when it starts up is the URL that you can use to connect to the server. So you always have the option to just grab that and paste it into a window. And it should get you the same thing. It'll get you back to this. Any problems getting Jupyter up and running? Okay. If you would, take a couple minutes to read through the Chapter 10 preview, run the examples that are there. I'll come around and help you out with any technical problems, and then we'll resume in a few minutes. Okay, let me walk through this notebook. This is, at the beginning of the workshop, I'm telling you everything that you're going to understand at the end of the workshop. So if this example doesn't make sense yet, that's okay. But I wanted to use it as a motivation for what can we do when we have all these ideas that we understand, what can we do with them? Here's one example, which is when you record a gunshot or any other sudden impulse kind of sound in a room, the response that you get, the recording that you get, characterizes the room. It tells you everything that you need to know about the acoustics. And you can use that recording now to simulate what it would sound like if you take something like this violin recording and play it in the room where the gunshot was recorded. So here's the theory. So I've got this gunshot. If I play the gunshot, it sounds like a loud sudden noise in an echoey room. If you play the violin recording, it just sounds like a violin recording in kind of an ordinary sounding room. And now the magic operation that we're performing here is convolution. And I'm going to explain what convolution is, so don't worry about it for now other than it's the magic. And the output, the result of convolving those two signals together, sounds like this. So that sounds like a violin being played in an echoey kind of a room. And you could imagine, you can almost visualize what that room might look like. To me, it sounds like a pretty large room that probably has pretty hard walls. And maybe it's even a long, thin room. And I'm not sure about that, and maybe I'm letting my imagination get away from me, but it kind of sounds like a firing range, which is, I think, where the gunshot was actually recorded. So this is simulating what the violin would have sounded like if it was played in a firing range instead of somebody's living room, which is, on the face of it, kind of black magic. And if this example seems crazy, it kind of is. Hang on a second, I just need to get back to advancing my slide. There we go. All right. Here are the three pieces that you have to understand to know why that example works. And this is the sequence of topics that we're going to do between now and about 4:20. So we're going to do the discrete Fourier transform, convolution theorem, which is the basis of that convolution operation, and linear time invariant theory, which sounds scary, and I'll explain that when we get to it. So part one, signal processing. We're going to do the Fourier transform. We're going to do it using thinkdsp.py. I mentioned this is a library that I wrote that goes along with the book. It's mostly just a thin wrapper around SciPy, and it's mostly just a thin wrapper around Fast Fourier Transform, or FFT. So there are three objects we're going to work with. One of them is a signal, and that represents a continuous mathematical function that exists over all time. So it's a pretty abstract kind of mathematical thing. A wave is a more concrete thing. It is kind of like a recording where you have samples at equally spaced intervals in time. And if you picture an MP3 file or a wave file or anything like that, basically any kind of digital recording of sound, that's basically what the wave object represents. And then the third piece is a spectrum, which is going to contain the Fourier transform of the wave. So we're going to go back and forth between signals and waves, and then from a wave you can compute a spectrum. From a spectrum you can go backward and compute a wave. We're also going to look at spectrograms, and I'll explain what that is in a couple of minutes. But this diagram, these are all the objects that we're going to work with today. If you get into chapter 1.ipynb, it'll give you an overview of those objects and how they work. So if you load up that notebook, read through the first section, and stop when you get to the section that's called interaction. And we'll resume in a couple of minutes. when you get through the notebook, there's an exercise on the next slide that you can try out. The idea is to construct a signal by adding up a bunch of cosines and sines, and then plot the spectrum of that signal and see what it looks like. Okay, let me grab you for a minute. I want to walk through the exercise, and then we'll come back and look at the filtering part of the notebook in a couple of minutes. So up at the top, the first few cells, cell number 2 creates 2 signals. One of them is a sine and one of them is a cosine. And you can plot what the cosine signal looks like zoomed in on a pretty small scale. So this is about 6 milliseconds of time. And this is the sine wave on roughly the same scale. This is about 3 milliseconds of time. The addition operator kind of does what you'd like it to do, which is it'll take 2 signals and it produces a mixture signal that now has 2 frequency components in it. And if you plot it, it looks like that. So instead of looking like a simple sinusoid, it's now a waveform that is a little bit more complex. And in general, as you add more frequency components to a signal, the waveforms start to look like more and more not simple geometric kinds of shapes, but crazy looking waveforms. And now if you have a signal, so mix is a signal object, you can use a signal to make a wave, then you can use a wave to make a spectrum, and then you can plot the spectrum. And the spectrum of this mixture looks like this. It's basically 2 spikes. Each of those spikes represents 1 frequency component. The height of that spike represents the amplitude of that component, which is like the loudness. So if you remember what we created, there are 2 parts at 440 and 880 hertz. And one of them is twice as loud as the other. And if you look at the spikes, they are at 440 and 880 hertz, and one of them is twice as high as the other. So there's this direct correspondence between the frequency components that make up the signal and what the spectrum looks like. Each spike in the spectrum corresponds to a frequency component in the signal. And that's what spectral analysis is. That's taking a sound or a signal and figuring out what frequency components it contains and how loud each of those frequency components is. And it's a theorem of spectral analysis that any signal can be expressed as the sum of a bunch of sines and cosines, signals that have exactly 1 frequency component in them. So that's part 1. That's one of the things that's in the notebook. The way that's done, the way you get from a wave to a spectrum, is in this example a discrete Fourier transform. It's discrete because the wave, instead of being a continuous signal that exists at all points in time, is a discrete sequence of samples. So we're doing the discrete Fourier transform. I'll get a little technical. Technically, what we're computing is the discrete Fourier transform. The way we're computing it is by using the fast Fourier transform algorithm. So DFT is the thing, FFT is the algorithm, but people use these terms interchangeably, so I'm not going to make a big deal out of it, but now you know. The function that we called, which is the wave class, provides make spectrum. It's just a wrapper around numpy.fft, which is the package that contains all the Fourier transform stuff, and RFFT is for real. The R stands for real as opposed to complex. So by and large, if you record something in the real world, if you take a measurement from the real world, the result is a real valued thing. So sound recordings are basically real, not complex signals. That's why we're doing that. Here's what the code looks like. You can see that the first line of the function is the one that's really doing all the work. I'm just calling our FFT, that computes the DFT. The rest of it is computing what the range of frequencies is that correspond to each of those amplitudes. So the spectrum itself contains 2 objects. It contains 2 numpy arrays. F's is the sequence of frequencies, and H's is a sequence of complex numbers that represents the amplitude of each frequency component. We're going to come back and I'll tell you more about what H's means and how it's unpacked. I do want to say one thing about how the DFT works. I'm not going to explain this in a lot of detail, other than to say it's basically correlation. If you want to know how much your signal is like a given frequency, one way to do that is just compute a simple sinusoid that's at a particular frequency. So if I have my signal and I have a sine wave at 100 hertz, If I compute the correlation of those two things, it will tell me how much is my signal like a 100 hertz. And then I'm going to repeat that. I'll say, how much is my signal like a 200 hertz? And that's what this diagram is intended to show, is I am comparing my signal to each of the frequency components I'm interested in, and the correlation that I get back is the amplitude of that frequency component. That is, there's a little bit of mathematical work to make that efficient, but that is basically how DFT works. The next thing that's in the notebook is about filtering, which is modifying a signal, and in particular, the filter that we're going to look at first is a low-pass filter that's going to break a sound up into its frequency components and then attenuate all the high-frequency stuff. Attenuate is the opposite of amplify. So instead of making that stuff loud, I'm going to make it really quiet. So all that's left is the low-frequency components. And I'll give you a minute if you want to get back into the notebook. You can run through the filtering part of the notebook, and then when you get to the last section, you should have an interact widget that lets you play with the filter. Give me just a second to get there. All right. So what this gives you is these three widgets. You can specify where you want to start the recording, how long the section is that you want to look at, and it will show you what the spectrum looks like for that little snippet of the recording. And then you can play it and hear what it sounds like. So that's a chunk of the recording. I'm actually going to make that a little bit shorter. You may not have the sliders, depending on your environment set up. Interact may or may not work for you. I'll come around in a minute and see if I can help. If it doesn't work, it's not the worst thing. You don't need to do this, but it's kind of fun to play around with. In particular, what you can try out is to play more or less the original sound, and then gradually turn down the cutoff frequency. So if you turn this down to about 3,000 hertz, what that says is that any component, so 2,700, close enough to 3,000. Any frequency component that's higher frequency than that is going to get dropped out of this signal. This is more or less what a telephone line does to sound. And if you play this, it should sound a little bit like a violin being played over a telephone. Or maybe over a really bad phonograph or something like that. And if you turn it down even more and cut off everything, let's say 1,000 or 1,500 hertz, something in that range, it sounds more and more like a violin being played in the next room, like you're hearing it through a wall or through water or through a pillow. And the reason is that almost everything in the world behaves like a low-pass filter for sound. In fact, that wall is a good example. There's a reason that there's soft padding on that wall, and it is that it makes that wall behave more and more like a low-pass filter with a very low frequency cutoff. So the only thing of mine that they can hear next door is the part of my voice, which hopefully isn't too annoying to them. And if you listen, you can just barely hear the people on the other side of the wall. So that's part 2 of the notebook. I'll give you just a minute to finish working through that. If you'll just give me a signal and let me know when you're done with this notebook, we'll move on to the next section. Okay, just to summarize what we saw in the first notebook, again, we've got spectral analysis, so we can take a sound, split it up into its frequency components, and that's what a spectrum is. And then we've got this idea of a low-pass filter, or in other kinds of filters, where we can modify the spectrum of a signal by either amplifying or more often attenuating some of those frequency components. Next thing I want to look at is this idea of the relationship between the waveform, what we see when we plot the signal varying in time, and the set of harmonic frequency components that make up that signal when we look at the spectrum. So whenever you're done with chapter 1, you can shut that one down, and then start up chapter 2.ipynb, and read through just the first section, which is called Waveforms and Harmonics. I'll show you a Jupyter Notebook trick that I often use on a laptop. Since you have a small screen, if you turn off the header and turn off the toolbar, you get a little bit more vertical space, which I think makes it a little bit easier to work with. So as you're working through this, I have a puzzle for you to think about, which is there's a triangle wave in the notebook that has this spectrum. There's a square wave that has this spectrum. And there's a sawtooth wave that has this spectrum. And you can organize them like this. So some of those signals have only odd harmonics in them. So the square wave and the triangle wave have, let's say if your fundamental frequency is at 100 hertz, you would have 100, 300, 500, 700, 900, but you wouldn't have any of the even multiples. So that's what I mean by odd harmonics only. The sawtooth, which looks like a ramp going up, has both the even and odd harmonics. Okay? The other axis here is whether those harmonics drop off quickly or slowly. So the square wave and the sawtooth, they drop off slowly, which means that there's still lots of amplitude at high frequencies. The triangle wave drops off very quickly. The first couple of harmonics are not very loud, and after that, they're practically non-existent. So we've got kind of 3 out of 4 quadrants that are occupied, and my question for you is see if you can think of what the waveform might look like that occupies the lower right-hand corner, meaning that it has both even and odd harmonics, but they drop off fast in the same way that the triangle wave does. Think about that. We'll talk about it in a couple of minutes. Okay. I'm not going to tell you the answer to this question. It's kind of interesting. I'm going to let you think about it. By the end of the talk today, you might have some ideas about how to do it. And if you don't, you're welcome to open up the Chapter 2 solution notebook. Has the answer to it. This is one of the exercises in the book, and so you can take a look. There are a couple of ways to figure out what belongs in that lower right quadrant. But moving on for now, the next topic that's in the notebook is aliasing. So if you will move on to Chapter 2. And take a look at that next section that's called aliasing. And again, we'll come back in a couple minutes and talk about aliasing. All right, let's talk about aliasing, and then we'll get back to the interaction that's at the end of the notebook. The fundamental idea here is that when you go from a signal to a wave, you are losing information. A signal is continuous in time, so in some sense it contains an infinite amount of information. If you actually want to record that, if you want to record a signal in a computer, you have a finite amount of information. When you take discrete samples, there are things you don't know anymore. And here's the example. If I am taking samples at 10,000 hertz, so I'm taking a sample every 10th of a millisecond, if I have two signals, and one of them is just a pure sinusoid at 4,500 hertz, the other one is a pure sinusoid at 5,500 hertz, I've chosen those two examples because the samples that you get are exactly the same for those two signals. So if you heard this, because we hear continuous sound in the room, you would hear two different pitches. But after you've taken discrete samples, there is now no difference at all between those two signals. And that's the reason it's called aliasing, is that you have two different pitches that are behaving as if they are the same pitch. It's sort of like having two names for the same thing, like having an alias. In this example, the sample rate is 10,000 hertz, and for reasons that I won't explain, that means that the highest frequency that you can still distinguish is 5,000 hertz. Anything above 5,000 hertz, like the 5,500 that we were looking at, looks as if it were a lower frequency. So the 5,500 gets folded and becomes 4,500, or it seems as if it is 4,500. The reason it's called folding frequency is that you could imagine that if you took the whole spectrum, as if you had done perfect sampling, infinite sampling, all the high frequency components get folded over back into the range between 0 and 5,000. So 5,500 becomes 4,500. 6,000 sounds like 4,000. Let me see if I can keep this up. So like 9,000 would sound as if it were 1,000. So what would 10,000 sound like? 10,000 would fold back and land on 0. 0 frequency is kind of a weird thing. 0 frequency wouldn't have any sound because it doesn't vibrate. It doesn't cause our ears to vibrate. We don't hear it. 0 frequency corresponds to moving the whole signal either up or down. It's sometimes called a DC offset or a bias. If you just take a signal and add 1 to everything, that would be a 0 frequency component that you've added. So 10,000 wraps back around to 0. Where does 10,001 go? Seems like it would go to -1, and it sort of does. There are negative frequencies. Negative frequency kind of makes sense, but another way to think about it is that that -1 now wraps around again and comes back to 1. So the whole thing kind of zigzags back and forth between 0 and 5,000 hertz. So that's how aliasing behaves. If you play around with the interaction, I give you a chance, if all the way at the bottom of the notebook, to take, I think it's a sawtooth, I forget what the example is. Yes, it's a sawtooth. So this is just a signal that has lots of nice high frequency components. And you can change what the fundamental frequency of the signal is. So let's maybe just crank that up to 500. Okay. So this is a 500 hertz signal that's being sampled at 10,000 hertz. So most of the frequency components are in the right places. I've got 500, 1,000, 1,500, and so on. Let me actually crank this up one more time. I'm going to go up to 1,000 hertz just to make the math easy. Okay, there we go. So we've got 1,000, 2,000, 3,000, 4,000, 5,000. There's also a harmonic at 6,000, but that has been reflected back and it overlaps with the 4,000. So this doesn't sound too bad because the high frequency components are kind of in the right places. It's reasonable. But this only works because the frequency of my signal happens to be a multiple of my sampling frequency, or maybe the other way around. But it's a nice even multiple. If I change the frequency just a little bit, now all of those high frequency harmonics that have been aliased no longer overlap with the harmonics. And if you take a sound that has this nice simple harmonic structure and add a whole bunch of extra frequency components to it, it sounds very different. In particular, when it was 1,000 hertz, it's kind of a very simple sound. It doesn't sound like it has a lot of complexity or richness because it doesn't have very many frequency components. If I have all that aliasing going on, now I can hear a bunch of low frequency stuff that's not supposed to be there. Okay. So play around with that a little bit. See if that makes sense. And then I'm going to suggest we're going to take 2 breaks roughly every hour. We're just about 1 hour in now. So why don't you play around with that notebook? We'll take a break and we'll come back at 2:30 on the nose. Okay, we are back. So I want to come back to this slide. We saw this earlier. This is my function called makeSpectrum that's really just calling our FFT to do the Fourier transform. And I kind of glossed over a minute ago what exactly those H's are. I said that they're complex numbers. Now I want to explain what that's about. So the spectrum has these two parts. F's contains the sequence of frequencies. For each frequency, there's a corresponding complex number, and it's usually called H just by convention. That complex number actually encodes two pieces of information, both the amplitude and the phase. We've been working with the amplitude. We're going to come back now and talk about phase. So if you are remembering complex numbers from some time in your distant past, you might remember that it is the sum of two parts, a real part and an imaginary part. And you can think of it as being a point in a Cartesian plane, where the x-axis here is the real axis and the y-axis is the imaginary axis. In the context of digital signal processing, we almost never care about the real part or the imaginary part. We don't think of this in terms of Cartesian coordinates. We think in terms of polar coordinates. So that same point in the plane can also be described by a radius r and an angle theta, where the angle is measured from the positive x-axis going in, I guess, the counterclockwise, yes, direction. And those two pieces of information give you the magnitude and phase. Not sure what happened with my Unicode there, but you get the idea. One way to think about this is if you're talking about a pure sinusoid, so just one frequency component, the phase is where in the cycle you start. Or equivalently, on the x-axis, where you just slide back and forth in time. So, yes. So in fact, if you take a sine and a cosine wave, they are separated by 90 degrees, or I guess that's pi over 2 in radians. And so yes, those would be equivalent. A shifted sine wave is just a cosine and vice versa. Good. Okay. Back into chapter 2.ipynb, there's a section there that's called amplitude and phase, and it's partly experimenting with if we change the amplitude, we know what that sounds like. More amplitude, more loud. My question is, what does phase sound like? If you change the phase of a signal, how does that change the sound? So play around with that. We'll reconvene in a couple of minutes. So let me walk through a couple of things here. I started with a sawtooth again. There's what it looks like. So the waveform of the sawtooth again. And the spectrum looks like what we've seen before. If you plot the amplitudes, this is what we were looking at before. This tells you how loud each frequency component is. If you plot the phases, you kind of just get a mess. And if you make most natural recorded sounds and look at the phases in a plot like this, it doesn't tell you much. So most of the time people don't bother to plot phase at all, but it got me thinking about whether there's information encoded in those phases that's important. And one way to check to see whether something's important is to scramble it and see what breaks. So I used random.shuffle to just take all those phases and move them around between frequency components. So if anything's going to mess up this sound, that ought to do it. And if you now take that spectrum and convert it back into a wave, it looks like this. And now every time you run it, you're going to see a different random-looking waveform. This looks visually very different from that sawtooth that we started. If you compute the spectrum of this, it will have the same amplitude for each frequency component, but it will have totally different phases from the original sawtooth. And if you listen to it, the original sounds like this, and the totally scrambled phases sound like this. To my ear, those sound a little bit different. It sounds like the scrambled one has had a little bit of a low-pass filter. It sounds a little bit muffled. But they sound more similar than I expected them to sound, because the waveforms look totally different. But they sound pretty close to the same to us. I'm not sure why they don't sound exactly the same. I think there's some interesting stuff to experiment with here. If you want, I've got another notebook in there that's called phase.ipynb, where I play around with this experiment some more. We're not going to do that now. We're going to move on. But I just wanted to pose this as a little bit of a puzzle. What does phase sound like? I think the answer is mostly we don't hear phase. But I think sometimes we do a little bit. I'm still a little bit unclear on this. So I'm just putting that out there as a puzzle to think about. But for now, we will move on. Everything we've looked at so far has been a signal that has the same frequency over time. Nothing's changing. And obviously things like speech and music and natural sounds vary over time. So pitches go up and down and all sorts of things. We're going to look at a structured kind of sound called a chirp, where the frequency changes over time, but in a sort of consistent pattern, usually increasing or decreasing linearly over time. So we'll look at chirps. If you open up chapter 3, read through the first section, which is called chirp. We're going to skip over leakage. Let's not talk about that today. And get to the third section, which is called spectrogram. And we'll go over it in a couple minutes.
Here I'm going to
Okay. If you've had a chance to play with this, you've heard what a chirp sounds like. So that's moving linearly from 220 hertz, which is relatively low on the piano, up to 880 hertz. So that's a 2-octave sweep. If you look at the first part of the curve, it looks like this. It's at relatively low frequency. The end of that waveform looks like this. Clearly, it's a higher frequency. I think I won't talk about exponential chirps today. So moving on, if you take something that's actually a chirp and plot its spectrum, it looks like this. The lower end of that is at about 220 hertz. The high end is at about 440 for this one. So this is a little bit different from the one we listened to. And what it's telling you is that this sound has an equal amount of energy at all the frequencies from about 220 to about 440, but the spectrogram is not telling you how that energy is spread out in time. From looking at this, you can't tell whether this is going up or down in pitch, or it could go up and down, and this would all look the same. So if you want to know both the frequency components and how those frequency components are changing over time, one way to do that is to take your long signal, this one is about a second long, break it up into a bunch of small chunks, and compute the Fourier transform for each of those chunks, and then plot those little spectral slices one at a time, and that's exactly what a spectrogram is. So if you take a look at this one, so this is a spectrogram where I've taken each little chunk with 512 samples in it and computed a spectrum. And now instead of plotting the spectrum on the x-axis, frequency is now on the vertical axis. And the darkness of that dot is amplitude. So what that's showing, all the way on the left-hand side of that figure, is the 0 time element. So the piece of time that's the first 512 samples. And the peak at the beginning is at 220 hertz. The peak at the end, at time equals 1, is at 440 hertz. And you can see visually that this is increasing linearly in between. But I made an arbitrary choice there. When I broke it up into chunks that were 512, I could have made that bigger or I could have made that smaller. And what you're going to get is a trade-off between how precisely you can track time and how precisely you can track frequency. So the next two examples, this one takes longer chunks of time, and what you get then is instead of 512 samples, you get 1,024 samples. So you get more information about what the frequency components are, and the vertical axis now is sliced up into finer little pieces. So the cells, the little rectangles that I'm plotting there, are now wide and not very tall. And that's a visual representation of the time precision and the frequency precision. So small is good. So here I have lots of frequency precision but not as much time precision. And here's the other way around. Lots and lots of little tiny samples. So I can distinguish things that vary very quickly in time, but I can't give you the frequency with a lot of accuracy. And that trade-off is called the Gabor limit. And what it tells you is that you can either have precision in time or you can have frequency in frequency. I think I didn't say that right, but you get the idea. But you can't have both. Graphically, you can think that the area of those little cells is a constant. But you can have a cell that's square or low and wide or tall and thin. Make sense? Okay. There's one kind of fun example that I just want to show you quick, which is the chirp that we just listened to was a sinusoid chirp. So when we plotted the beginning and the end of the chirp, it basically looks like a sinusoid just with the frequency changing. And the spectrogram just has one frequency component in it. But if you will open up Chapter 3 solution, one of the exercises was to make a sawtooth chirp. So a sound where the waveform looks like a sawtooth, but the frequency increases very linearly over time. And I love this example just because I did it just for fun, and it turned out to be much more interesting than I thought. So there's what the spectrogram looks like for a sawtooth chirp. Each vertical slice here has not just one frequency component like the sinusoid. It has the fundamental frequency, which is the loudest, but it also has all the integer multiples, which are the harmonics. And you can see that fanning out pattern is the harmonics spreading out in frequency as the fundamental frequency increases. If you look very carefully, you can see that some of the high frequency components get aliased. That when they come up against the top of this figure at 5,000 hertz, that's the cutoff frequency, they reflect back down. You can't see it very clearly on the projector, but you might be able to see it on your laptop. So that's what the spectrogram looks like. And now here's what the thing actually sounds like. And I thought, when I played that for the first time, that's a cool sound. It sounds kind of familiar. It sounds like the red alert signal from the original Star Trek series, which I found a recording of. So here's what that sounds like. And it's a little different. The quality of the recording isn't very good, but I think it's basically a sawtooth chirp. So I was very excited when I discovered that, because it kind of makes sense that in 1968 that would be the kind of thing that you would get out of a simple sound synthesizer, sawtooth chirp. And of course, if you're dealing with an emergency situation and you need to make critical decisions quickly, what you really want to hear in the background is that going on, because that's going to help with the problem. Yes, please. Yeah. Let's see. So would a sinusoid, if you had a high frequency sinusoid and you were sampling at a low sampling rate, would you see those harmonics? You wouldn't see the harmonics because, again, that sinusoid only has one frequency component. But you would see that as that fundamental tone crossed the threshold, when it hits the folding frequency, it would reflect off the top of the spectrogram and reflect back. I might try that up here while you guys are working and see if I can get an example going. I have one other resource that I wanted to point you to, which is, this is a game you might enjoy playing. Now that you know what chirps are, like literally bird chirps, and you know what spectrograms are, this is sort of like a video game that will help you identify birds by sound. And what it'll do is it'll play the sound of a chirp, and then you have to match up which spectrogram is the spectrogram for that chirp that you just heard. It is a surprisingly fun game. So you'll have a chance to play that some other time, but not now. All right. We're going to move on to our next topic, which is smoothing and convolution. I promised to talk about convolution. That is sort of our second big chunk. So we now, at this point, we understand aliasing, we understand spectral analysis. Convolution is the next big idea. And I want to start with one particular use of convolution, which is from statistics. That very often, if you have a noisy signal and you want to find out what the overall trend is, you can apply a moving average. And a moving average, in this case, I think I did a 30-day moving average. And that just means I'm going to take the first 30 days and compute the mean and plot that as one of these blue points. And then I'm going to shift that by 1 day. So I'm going to compute days 1 through 31, compute the mean, plot a point. Shift again, compute day 2 through 32. And that gets me that blue line, which you can see the gray line there is more jaggy, more noisy. The blue line there is somewhat smoother looking. Anybody, by the way, know what that graph is? It is kind of a random walk. It is a stock price That is the price of Facebook since its IPO, stopping about a year ago, which is when I collected the data. So if you've done any kind of time series analysis in the world of statistics, you might have seen things like moving averages. You can do the same thing with signals. So you could apply a moving average to a sawtooth, which is the next example that we're going to do. And it's the same idea. The thing on the right-hand side there is called a window. And I think this is an 11 sample moving average. So for the first 11 elements, it is set to 1. And then you see that it drops down. All the remaining elements are 0. So if I multiply those two things together, if I multiply the window by the signal, I will get only the first 11 elements. And then I'll add them up. And then I'm going to shift the window 1 sample to the right, multiply again. That'll get me the next 11 elements, and add them up, and so on. So this is a way of describing a moving average by using an operation called convolution. And convolution is exactly what I just described. I'm going to take my signal and my window, multiply them together, add them up. Shift the window, multiply, add. Shift, multiply, add. That's what convolution is. I just described that here. If you want to see what that looks like in Python, it's basically this. So smoothed is a NumPy array where I'm going to put the result of the convolution. And rolled is going to be a copy of the window. So I'm going to start with that window on the right. Each time I apply the roll operation, it's going to shift the window 1 cell to the right. And then inside the loop, I'm going to multiply them together. That's the rolled times segment.wise. The wise, that's the waveform, the wise. And then add them up, that's the sum. Does that make sense in terms of code? Yeah.
So the first point gets the average of the next 10 days, right? Because you don't have the data necessarily from before.
Correct.
So is that window the same for the first 10 points then?
Yeah, so dealing with the boundary, the question is about how to deal with the boundary conditions, right? And so what do I do for the first 10 days? And the usual way to do this is I'm going to take just the first 10, compute the first value, and then I'm going to put it into the 10th location. So the first 9 locations would probably be empty.
So you lose that.
You just lose it.
Okay.
Yep. All right. To see how this works, I've showed you the code, but you're going to run it in just a second. Open up chapter 8 and do the first 2 sections, which are about smoothing, and then the second one is called smoothing sound signals. I'm going to let you get back to this in just a second, but I want to introduce the next section of the notebook is called frequency domain. I just want to introduce that section, and then I'll send you back to the notebook. So first thing, when you apply this window, this 11-cell moving average to a sawtooth, it kind of smooths the sawtooth out, not in a way where you obviously look at the blue thing and say, oh yeah, that looks a lot smoother, but it has smoothed a little bit, if not a ton. So visually, when you look at the signal, you get the sense, okay, it's a little bit smoother. Now the next thing we want to look at is what happens to the spectrum. When you apply a moving average, the waveform gets smoother. What does that mean for the spectrum? And I want to just introduce some vocabulary here. How many of you have heard of the time domain and the frequency domain? Okay, some people. The idea is we've actually been using these all along. When you look at the waveform, you are looking at a function of time. So the x-axis is time, and so it's called the time domain. When you convert to a spectrum, now you're looking at a thing that is a function of frequency. The x-axis is frequency, so it's called the frequency domain. Every time you go back and forth between these two representations, you're getting the same information. You're just looking at it in two different ways. If you give me a wave, I can compute the corresponding spectrum. If you give me the spectrum, I can compute the corresponding wave. So there's this correspondence between the time domain and the frequency domain. That idea turns out to be fundamental in all kinds of signal processing. That every time you do something to a waveform, you are also doing something to the spectrum. And you can visualize the effect in two ways. You can look at the waveform in time, you can look at the spectrum in frequency. So here's my conjecture. If we're smoothing something out, I suspect that we're doing something like a low-pass filter. That the high-frequency, jaggy, noisy bits of the signal are getting squished, and what's left is just the low-frequency, long-term trends. In other words, convolution with this window is having the same effect as applying something like a low-pass filter. But I would like to figure out what kind of filter it is, and we can do that by kind of looking at this picture to figure out what the middle looks like. So the top row is the time domain, and the bottom row is the frequency domain. The star symbol up at the top there is the symbol for convolution, and the X symbol at the bottom is what I'm using for multiplication. And this is visually what the convolution theorem is going to tell us in a minute. That when you apply convolution in the time domain, so in this case, I'm taking a wave and I'm convolving it with a window, and so I get a smooth version of my wave. In the frequency domain, what's happening is that my spectrum is getting multiplied by a filter, and I'm getting something like a low-pass filter. And you can see again the gray part there, those are the frequency components that are getting either eliminated or attenuated. But now I want to figure out what the middle part looks like. What is the filter that corresponds to this window? And I'm going to do it in a backwards way, which is if I think that a spectrum times a filter equals my result, then I can take my result and divide by the spectrum and figure out what the filter looks like. So spectrum 2 is the output. That's the right-hand side. Spectrum is the input. That's the left-hand side. So amps 2 divided by amps should tell me for each frequency component how much did it get shrunk by? What's the ratio of the output to the input? And this is kind of a crazy experimental way of trying to figure out what that filter looks like. I had to do one other little hack, which is in the places where the amplitude is big, I'm going to get an accurate measurement of this ratio. When the amplitude is small, it's going to be really noisy. So to suppress the noise, I just put a threshold on it. I said when the amplitude is low, we're going to just pretend there's nothing there. And that's just kind of a hack to make the visualizations work. But if you go back to the notebook now and read through the section on frequency domain, hopefully what I just said will make sense, and you will see a figure that looks like this. So this is what that result looks like. I computed the ratio of the output to the input for each frequency component of the input. And when you look at that, it's not really clear what that is. It is something like a low-pass filter because all the low frequencies, everything below 5,000, is going through more or less intact. And everything above 5,000 is getting attenuated by at least 80 or 90%. So it's kind of like a low-pass filter, but maybe it's not a very good low-pass filter because a lot of the high-frequency stuff is getting through. To figure out where that shape is coming from, we can go back to this diagram. Because again, we're trying to figure out what that middle box should look like. And remember that the top row here is the time domain, the bottom row is the frequency domain. So if you want to get from the wave to the spectrum, you compute the FFT. And if you want to get from the wave of the output to the spectrum of the output, you use the FFT. So what happens if we compute the FFT of the window? It seems like a strange thing to do, but if you've already run this cell, you have seen that gray line is the Fourier transform of the window. And the blue line is the amplitude ratio that we computed. And they match up pretty well. And what that's telling us experimentally is this. That the spectrum of the window is the filter. That if you want to know what effect this window has in the frequency domain, all you have to do is compute the Fourier transform of the window. And that is the convolution theorem. Convolution theorem states that when you, in the time domain, convolve a window with a signal, that corresponds to, in the frequency domain, multiplying a spectrum by a filter. And furthermore, the filter that you apply is the DFT of the window. So that's a lot of vocabulary at this point. I'm sort of using a lot of words, but this figure kind of summarizes the whole thing. This says that if you want to compute the DFT of a wave convolved with a window, you can do that by computing the DFT of the wave and the DFT of the window and multiplying them together. Graphically, here's one way to think about that. The left-hand side of this equation corresponds to the orange arrow. That says I'm going to convolve the wave with the window and then compute the DFT. So that's like going across the top row and then down. The green arrow corresponds to the right-hand side of this equation. That says you can compute the DFT of the wave and the DFT of the window and multiply them together. And the convolution theorem says that whether you go the orange way or the green way, you get the same result. This figure was my best attempt to explain the convolution theorem in one slide. So I'm hoping that makes some sense. It may not be perfect at this point, but we'll work with that for now. So that's the convolution theorem. One reason why this is a useful thing is because we have the Fast Fourier Transform, we can compute DFTs in n log n time. If you've taken some computer science and you know about big O analysis of algorithms, this will make sense. If you've never heard this before, just tune out for a second. I won't have time to explain it, but to get from the top row to the bottom row, I can do that in n log n time. So the green line here is two Fourier transforms that are n log n, and then the element-wise multiplication of two vectors, and that's linear, that's n. So the green line here takes n log n time total. The orange line usually takes n squared time, or quadratic. So Fast Fourier Transform plus convolution theorem gives us efficient ways of doing a lot of computations like this that go back and forth between the time domain and the frequency domain. Yes, convolution in the time domain is more complicated than just multiplying the two vectors. It's the simplest way to implement convolution is the way I showed, which is that you multiply the wave times the window. That gets you 1 point, and then you have to shift the window, multiply again. So there are n steps, and each step is linear, so that's how you get the quadratic. Okay. So what we discovered is that when you apply this boxcar window, it's called a boxcar because what that window looks like visually is just a square lump on a railroad track. And when it rolls along, it moves along the railroad track. So the boxcar filter, which is also a moving average, is kind of like a low-pass filter, but as I said a minute ago, it's not a very good low-pass filter. Part of the reason it's not very good is because it looks like a square wave. When you compute the DFT of a square wave, you remember we get slowly decaying harmonics, and that's what that bumpy window is. This bumpy filter is the slowly decaying harmonics of a square wave. Okay. So if a really sharp window, like a boxcar, yields a filter with slowly decaying harmonics, one way to make it better is to make it smoother. If your window is not quite so sharp in the time domain, your filter will be sharper in the frequency domain. So here's my claim, and again, we're going to verify this experimentally. Instead of a boxcar, which is this rectangle that cuts off sharply at the corners, I'm going to use a Gaussian window, which is a nice smooth curve that has a bump in the middle, and then it tails down to 0 with nice smooth tails. And my conjecture is that a smooth window in the time domain will correspond to a nice clean cutoff in the frequency domain. And if you go back to the notebook, chapter 8, there's an interactive widget all the way at the bottom that will let you play around with this. Okay, I'm going to play around with this just a little bit. So the standard deviation is the standard deviation of the Gaussian window. So if you increase it, it makes the Gaussian window wider. So that makes a wide bell curve. If you decrease the standard deviation, it makes it narrower. The other parameter, m, is the number of places where we evaluate the window. So I started out with 11, but you can crank it up. You can have a nice wide window with lots and lots of points in it, or a small one that's only measured at a couple of locations. So let me stick with m equals 11 for just a second. When I have a low standard deviation, my window is not very wide. So I'm not adding up very many points. I'm not smoothing it out very much. And so I'm not filtering it very much. Lots of high frequency components are still going through. As I increase the standard deviation, the window gets wider, so I'm adding up more points. So this is like a moving average with a bigger and bigger number of points in it. So I'm getting more smoothing, so I'm getting more high-pass filtering, and so the cutoff frequency is getting lower and lower. So if I go from 1.4 to 2, now it looks like my cutoff frequency is down below 5,000 hertz. If I increase it more, let's go to 3, the cutoff frequency gets lower, But something else is starting to happen. I'm getting those bouncy high frequency components back. And the reason is that as the standard deviation gets wide, I'm getting an approximation of a Gaussian curve that's worse and worse. This is starting to look more and more like the boxcar filter. If the standard deviation is really wide, then it practically is the boxcar window, and so I have all that bounciness going on. But I can keep the standard deviation high and increase m. Now I have high standard deviation and a good approximation of a bell curve, and now I have a good quality low pass filter. This is keeping just a few low frequency components and everything else is getting cut off, and there's much less of that bouncy high frequency component left. And again, if I decrease the standard deviation, the window in the time domain gets narrower, and the filter in the frequency domain gets wider. So there's this inverse relationship between the width of the window in the time domain and the width of the filter in the frequency domain. Good? Questions? Thoughts? So just to summarize, the wider window in the time domain means more smoothing, which means I'm cutting off more frequencies. So it's a more aggressive low-pass filter. And then there's a little bit of a weirdness, which is that if the value of m is too small, my window starts to look like a boxcar. And when it looks like a boxcar, I get the bouncy frequencies back. It might be a good time for a break. So I've got 3:20, let's come back at 3:30 on the nose. I think we've got snacks out there, and if you have questions during the break, I'm happy to talk. we can get going again. Before I start the third section, it might be worth just taking a minute to do an inventory on the convolution theorem. Questions about this? Things making sense? Anything that you want to say or ask now before we move on and make things harder? Yeah? What would convolution be used for in an audio context? So one example is the example that we started with, which is using convolution to simulate what a sound would sound like in a different environment. And that's actually where we're headed for the third section. So that's one application. And then the other application is other kinds of filters. So in this example, we did a low-pass filter, but there are high-pass filters and notch-pass filters and other kinds of things that you can do. Okay, other thoughts, questions?
So all those audio effects that application stack are just application of convolution.
So the question is, are the audio effects that you hear when you apply an effect to, using a sound processor or anything like that, are they all convolutions? The answer is that a lot of them are, but not all of them are. So every convolution in the time domain corresponds to a filter, but there are things that you can do to sounds that do not correspond to filters. And in particular, it'll be things that are non-linear. So everything that we're talking about here are linear filters, and I'm going to explain in just a second exactly what I mean by that, because you're both asking the perfect questions to segue into the next big topic, which is LTI theory. LTI stands for linear time invariant, and then we're going to talk about systems that have those properties. So what I mean by a system is anything that takes a signal as an input and produces another signal as an output. So things like sound processing hardware, you literally have a plug that goes into the input and a plug that comes out of the output, and that box is a system. But you can also think of this microphone going to those speakers as a system. What comes out of those speakers is not exactly what's going into the microphone. And in fact, what's going into your ears is not exactly what's coming out of the speakers, because it's being transmitted through the air in the room. The air in the room is also behaving like a system that has an input and an output. So a system is anything that takes inputs and outputs, and LTI system has these two properties, time invariance and linearity. Time invariance means that the behavior of the system doesn't change over time. So if I put in a particular input now, and I see a particular output come out, and then I come back tomorrow and do the same thing, the same input will yield the same output. And I can shift, I can come back tomorrow, I can come back a year from now, time invariant. That's part one. Part two, linearity, means that if I put two signals in at the same time, the outputs will be the sum of the outputs. So I could run an experiment where first I put in input number one and I measure output number one. Then I come back later, I input number two and I measure output number two. And now for my third experiment, I put input one plus input two. So with sound, addition basically just means playing two sounds at the same time, adding two signals to each other. The output, in that case, will be the sum of the outputs. Or I should say, if the output is the sum of the outputs, then that system is linear for any inputs. And this is somewhat restrictive. There are lots and lots of systems in the world that are neither linear nor time invariant. So for example, basically, if anything in the room is moving, then this will not be a time invariant. So if that wall were vibrating, then the sound of my voice would sound different depending on whether I happen to catch it moving out or moving in, all kinds of crazy things. But by and large, if the room is not moving, then the path for sound between any 2 points will be pretty much like an LTI system. So acoustics, by and large, are LTI, or at least close enough to be a good engineering approximation. I want to give you a little bit of intuition for what that means. you already have some intuition. You know what acoustics can do. So if you play a sound in a concert hall or anything else like that, you know that the LTI system can delay the signal. It takes time for sound to propagate across a room. It can echo a signal. So in fact, you're hearing echoes right now. You're hearing many copies of my voice because you're hearing it in a direct path from me to you. You're hearing it from the speakers to your ear. You're hearing it from the speaker to the wall to your ear, and so on. And that's why it has a kind of a reverby sound. Okay, so I can delay a signal, I can make echoes. I can also do things like low-pass filters by attenuating some frequencies more than others. So again, we talked earlier about what I sound like next door and what they sound like here. We're hearing just a little bit of that low frequency from next door coming through. But two things that LTI systems don't do. One is they don't output more energy than you input. So amplifiers, for example, don't count. And the other thing is that they can't move energy from one frequency to another. So if I play a perfect sinusoid at concert tuning A, which is 440 hertz, you might hear that loud, you might hear it quiet, you might hear it delayed, you might hear echoes of it, but you will not hear any frequency other than 440 hertz. And again, you have some intuition for this. There aren't rooms in the world where you can sing at one frequency and hear a different frequency. There are mechanical systems that do that. In fact, this is a diagram from a patent for a frequency doubler, which is a mechanical system that if you put a vibration into it at one frequency, the output is at double the frequency. It's kind of cool that that exists, but that's an example of a system that is not LTI. Okay. What all of this means is that if you can figure out the effect of the room on each frequency component separately, then you know what the room does to all the frequencies, and you can figure out what that room would sound like for any arbitrary input. Okay? Because if I tell you that this room will always attenuate 440 by this much and 880 by that much and so on, then you could take any recorded signal, break it up into its frequency components. You could play those frequency components one at a time, find out what happens, and then put them all back together again. That's what LTI means, is that you can break it up, play it one at a time, and go back. And if you know that, you know everything there is to know about the room from an acoustic point of view. And this is what people actually do. If you're designing concert halls or if you want to simulate the sound of a particular room, you can go to that room and make measurements. You can characterize the room. And what characterize means is I know what the filter is. I know what effect the room has for every frequency component. And there are a couple of ways to do that. And one of them is what I said a minute ago, input one frequency at a time. So you can imagine just playing sort of like a piano, but a piano that makes perfect sinusoids. So the actual sound of a piano is kind of complex. It has lots of harmonics. But pretend we have a real synthesizer that just plays sinusoids. I could just play every note on the piano one at a time, record the results, and I would know everything there is to know about the room. At least for the discrete piano keys. Maybe here's another idea. If I wanted to know all the frequencies, not just the discrete piano keys, I could play a chirp. I could play a sound that goes boop through a whole range of frequencies, and if I record the output, I would be able to characterize the room. Both of those are actual methods that people use, but there's one other way of doing it that's kind of cool, which is, again, it's an LTI system. So there's no difference in my measurements between putting the frequency components in one at a time or putting them all in at the same time. So what if I can make a sound that contains all the frequency components? What would that look like? I don't know. I know what the spectrum looks like. That. So I want to generate a sound that has that spectrum. That spectrum is flat, equal power at all frequencies. How can I figure out what that waveform looks like? I know how to get from a wave to a spectrum. How do you get from a spectrum to a wave? Reverse the FFT. Reverse the DFT. We know how to do that. Mathematically, it actually turns out to be the same. The DFT and the inverse DFT are actually the same operation. It's kind of weird. I'm not going to show you that today, but check it out at some point. So if you know what spectrum you want, you can assemble the wave that has that spectrum just by computing the DFT, and that's what it looks like. Now, this is not at all obvious to me. Maybe it's obvious once you understand this in more depth, but I'm just going to take this, if you'll let me, just take this as a given, that that is actually the DFT of a flat spectrum. And what it is what's called an impulse. It is one sharp, sudden sound at t equals 0 and then nothing from then on. What that means is that if you input an impulse to a system, you are inputting all the frequencies at the same time, and the output will be a summary of the system response to every frequency. And in practical terms, what that means is that you can go into a room and clap or pop a balloon or fire a gunshot, depending on the circumstances. And if you record the result, you know everything there is to know about the room acoustically. So just to get the vocabulary, the input is called an impulse. The output is called the impulse response. So that's the response of the room, the output when you input the impulse. And if you now take the Fourier transform of the impulse response, that thing is called the transfer function. I'm going to come back, I'm going to show you this diagram now, and then we'll get into the notebook. So this is the wave on the left. That's the violin recording we heard at the beginning. The window now is the gunshot. I'm using another signal as a window. And if you convolve the wave with the window, you get this output, because what you've done is you've multiplied the spectrum, the input spectrum, by the filter. Now, the only thing, I'm changing the vocabulary a little bit. So when we were talking about smoothing, I talked about a wave and a window, and a spectrum and a filter. In the context of system characterization, I'm changing the vocabulary just a little bit. So the window is now the impulse response. Window becomes the impulse response, and the filter is called the transfer function in this case, because it tells you how the input is being transferred through the system into the output. This diagram will make a little bit more sense after you work through the chapter 10 notebook. So open that up, run through the first two sections, skip the first two sections and run the section that's called acoustic impulse response. But don't forget to run the first cell, because otherwise you don't have your inputs. Sorry, imports. just got an interesting question. When you go from a spectrum to a wave, the spectrum is just a range of frequencies. And then you get the wave, and the wave has a duration in time. It's a certain number of seconds. And the question I just got is, how does the spectrum know how long the corresponding wave was? And the answer is that the spectrum object contains both the frequencies and the H's that contain the amplitudes. And because I know the frequencies, I know what the spacing must have been in time. I can figure out, going backwards, how much space in time there was between the samples. And by looking at the length of the spectrum, I know how many samples there were. So taking those two things together, I can back out how long the original recording was, the duration. If you get a chance, is it assuming a given frame rate? Yes, so that's right. And if you look inside the spectrum object, it records its frame rate. I think. I'm trying to remember. It might be explicitly stored, it might be inferred. I forget, we can look at the code. Okay. I just want to walk through this example. We saw it at the beginning, but hopefully it's making a little bit more sense this time around. So again, when we have a recording of a gunshot, what that recording is telling us is the output of the system when the input is an impulse. Or at least we're assuming that a gunshot is very close to being an impulse. Mathematically, or in physical terms, you can't have a perfect delta function. It always has some duration in time. But if it's a good approximation, then this should be a good approximation of the impulse response. And if we compute its DFT, we get this, which is the transfer function. And what that is showing you is partly what effect this room has on each frequency component. And like practically everything in the world, it looks like a low-pass filter. The low frequency stuff is not being attenuated very much. The higher frequency stuff is being cut off. There's actually more information here than I'm showing. Remember again that there's phase information. So this tells me what happens to the frequency components. The phase information tells me how much things are shifted in time. So both of those things are happening. In fact, those are kind of two ways of thinking of the same thing. So here's what that transfer function looks like. There's what it looks like on a log scale. And now if I take a signal like the violin recording, I can compute the DFT of the violin. And now I've got these two spectrums that are the same length, because I kind of tweaked it to make them be the same length. What that allows me to do now is multiplication. So this is just element-wise multiplication of two Fourier transforms. I took the Fourier transform of the gunshot, that's my transfer function. I took the Fourier transform of the violin, that's my input spectrum. I'm going to multiply them together element-wise. The result is now the spectrum of the output, and to get back to the time domain, I'm going to use make wave. And that output should sound like the output of the violin played in the room where the gunshot was recorded. Yeah. Where is the phase information stored? It's in the H's. So remember that we get these complex numbers. When I plot a spectrum, I'm just plotting the amplitudes, I'm not plotting the angles. But it's still stored in the spectrum object, right? And if I didn't have that information, this would not work. So this is an example where the phase really does matter. If I did that experiment from a couple of notebooks ago where I scrambled the phase, this output would not sound right at all. So the question is there a good graphical representation that shows both the amplitudes and the phases? The answer is no, or at least not that I'm aware of. I haven't seen a good representation of phase that means anything to me. Yeah? Yes. Yes, there are a few ways to do that. So the question is, I cooked this example so that the two inputs are exactly the same size, and that makes the computation easy because I didn't have to do any kind of fiddling around. There are a couple of ways to do it. So one is to assume that the impulse response is finite in its duration. In other words, that the gunshot, after some period of time, whatever echoes there are that are left are so small that I'm just going to round them off to 0. If I do that, then I can extend this impulse response with zeros out to an arbitrary point in time. And so then I can simulate any signal of any length. That gets to be computationally kind of bad. So conceptually, that's very clear, but it's not very good. The alternative is kind of similar to the spectrogram, which is I could take my signal and break it up into short chunks, and I could convolve each of the chunks and then reassemble the output. It gets to be a little hacky, but it's very doable. Good. Any other questions about this example? All right. If you would like to, let's take just a couple of minutes. The next section of the notebook explains a little bit more about how this works. The section called convolution. One way to think about what's going on is that the output from an LTI system is just like the input, except that it's been shifted in time and scaled, expanded or shrunk vertically. And so one way to see that is to work your way gradually up from something like this. This is the gunshot being played once and then being shifted in time and shrunk and played again. And on the face of it, it doesn't sound like very much. It sounds like 2 gunshots, where the first one is a little bit louder than the second one. That seems uninteresting so far. But if you have lots of these things, so instead of just 2 copies of the gunshot, I'm going to make 220 copies of the gunshot. And I'm going to shift them all by just a short period of time. And what you get is something like this. Okay? So that was 220 gunshots being played with just a few milliseconds between them. And it doesn't sound like gunshots anymore. It kind of sounds like a buzz at 220 hertz. So if my input is 220 hertz and I play 220 gunshots, I get kind of a buzz, and then I get the echoes, and the echoes are kind of what I expect. So now if my input is something like a violin recording, I think I haven't run this cell yet. The violin recording is just a bunch of little tiny impulses in a row. And every one of those impulses is going to produce an impulse response. And if I add up the impulse responses, and it takes a while because this is a wildly inefficient way to do this calculation, but when it does, it should sound like a violin being played in a firing range. Let's see. Oh, sorry, that was still the beep. Maybe I didn't do, oh, sorry, that was a very short segment of the violin. I had to do a very short segment of the violin because this is so wildly inefficient. But that is one note being played in a firing range. And there's what the spectrum looks like. But here's now the much more efficient way to compute the same thing. And because it's so much more efficient, we can do the entire recording. first one, I was doing things inefficiently by actually adding up shifted and scaled versions of the input. I was basically running a Python loop that looks like this. And the second one, so that's the n-squared algorithm. And the second one is using the convolution theorem so that instead of crazy multiplication, I'm just using this convolve operation. And actually, I'm sorry, I might be telling you the wrong thing. There are two versions of this. There are two ways to make this faster. One of them is to use NumPy to do the convolution. And that will still be quadratic, but it'll be a lot faster because NumPy is running in C. It's not running a loop in Python. And I think that's this version. The previous version is the one that used the convolution theorem. Okay. So hopefully that makes some sense. I want to take one more pause. I want to give you a minute to run through the notebook that I just did, see if it makes sense, ask me questions if you do, and then we will wrap up. Okay, so at the beginning, we looked at this example where we simulated a violin in a firing range, and I claimed that if you understand these three things, you will have a pretty good idea of why that example works. And the idea is that if we know that the system is LTI, linear and time invariant, we can use that gunshot to characterize the system, and then use that as a filter to figure out what the input, the violin, would sound like as an output being played in a firing range. And we were able to do that efficiently because of the convolution theorem, and we were able to make it work because you can take the input and break it up into its frequency components, and in some sense you're going to put those frequency components into the system one at a time, compute all the outputs, and then add them up. And that's basically what convolution does. Hopefully, this makes a good amount of sense now, but I would be very surprised if after 3 hours it's all totally clear. But I've done my best to write this down in more detail, so if you do want to read more, ThinkDSP is available under a free license, so you can download it and read it and pull out sections, whatever you want to do. And also, if you like paper, you are welcome to buy a copy from the good people at O'Reilly. If you have any questions for me, or if you want to follow up, here are some ways to get in touch with me. And then the last thing you should do before you leave is fill out a survey for the nice people who run the tutorials at PyCon, and let us know how it went. If you have feedback for me, I don't get the results from the survey, I don't think. So if you have feedback from me, if you would send that directly to me, that's great. But also do the survey. And if you don't mind taking a couple of minutes before you go, this would be a good time to do that. And I'll come around and answer questions too. But other than that, we are done. So thank you all very much. I appreciate it. Thanks.